Hello all, welcome to the new video of signals and systems. In this video we'll study about steady state error. So in the last few videos we studied about the importance of transient response and steady state response. So in the previous video I covered about the transient response of first order and second order systems. So in this video we'll concentrate on steady state response. So mainly when we are studying about steady state response, we concentrate on steady state error. For example, say you have applied a step input to a control system, then the output will be typically in this fashion. Okay, so this is the input, then the output will follow in this fashion. Okay, so as you can see here, this is the x-axis is time 0 to this is the time domain which is represented on x-axis, and this is our output in the y-axis. Okay, so this is the input r of t and this is the output c of t. So when a unit step input is applied to a control system, depending upon the value of zeta, one of the response will follow in this fashion. As you can see, from time 0 to up to this point, this part of the response is called as transient response, and what follows next from here till t equal to infinity or t tends to infinity is called as steady state response. So in steady state response you can see that the output is trying to reach the value of input. However, it is not exactly reaching the exact value of input. Say input is 1, however my steady state response graph shows that the output is say up to 0.98. Okay, so the accuracy of this control system, or we can say the efficiency of a control system, can also be determined by its steady state response. In previous videos we emphasized on the importance of transient response. Okay, so how fast your system responds to the input and what goes in the transient response, we studied about that. But also another type of response analysis of another type of response, in this case the steady state response, is also very important. You can see here my input is 1, however this control system can reach only up to the maximum value of 0.98. Okay, so this reveals the accuracy, how accurate is my control system, whether it can match the input, or if it doesn't match the input, what is the difference between the output and input. Everything can be analyzed by steady state response. Okay, so as you can see there is an error observed here, that is difference between input and output. So this error is called as steady state error. Okay, the error which is observed during steady state response is called as steady state error. So we know that this is r of t and this is c of t. Let's define the error as r of t, which is input, which is higher in this case, minus c of t. Okay, so we need to define the steady state error now. So we know the difference, there is a difference between input and output. So the steady state error is defined based on this. Okay, so it is represented by ESS, which is called as steady state error, equal to limit of t tends to infinity e of t, because this response go on forever till infinity. Okay, so for accurate results we need to define t tends to infinity, because in some cases the output may look stable here, but it may try to reach the maximum after say some time. Okay, so it is important for us to get the steady state error as accurate as possible. So in mathematical terms, we will take t tends to infinity because our response is defined from 0 till infinity. Okay, so this is the steady state error definition. ESS is limit of t tends to infinity E of t. So if you are familiar with the final value theorem, you can look up anywhere for that. What is the theorem says. So I'll not explain the final value theorem derivation here, but using final value theorem, we can define steady state error in this way as well. Using final value theorem, the steady state error ESS is equal to limit of s tends to 0 s e of s. Okay, because most of this control systems are represented in s domain. Okay, so it will become easy for us to calculate steady state error with the help of s domain. So this formula will be very useful for us. Okay, so this is the formula for steady state error. So as you can see, this is the typical control system. This is the RS input and G of S. This is our system which is having a transfer function of G of S, and this is unity feedback negative control system. Negative feedback control system with unit gain. So this is the output C of S. So we can get E of S from this control system model. Okay, so now what we'll do, we'll try to find out what is the value of E of S in terms of R of S, G of S or C of S. Okay, and then we can simplify this equation further, and then we can then define the value steady state error in general for any type of control system with unity feedback with negative feedback control system. Okay, and also we'll see what is the steady state error for different type of signals such as step input and then a ramp input or parabolic input. What is the steady state error? Let's calculate that. Okay, so let's try to simplify this block diagram and get the value for E of S. So let's simplify that. So from the control system block, we can write it as C of S upon R of S is G of S upon 1 plus G of S, because H of S is 1, since it is negative feedback with gain equal to 1 in the feedback. Okay, and we have E of S is equal to R of S minus C of S. So you can get C of S here, which is R of S into G of S upon 1 plus GS. Okay, so E of S will be R of S minus R of S G of S upon 1 plus GS. Say, so take R of S common here. This will become 1 minus G of S upon 1 plus G of S. Okay, so 1 plus G of S minus G of S, let's simplify this. This will become 1 plus G of S minus G of S upon 1 plus G of S. So this will get cancelled. We get E of S is equal to, I'll write it down here, R of S upon 1 plus GS. Okay, so my steady state formula now becomes, in S domain, I mean everything on the right hand side will be in the S domain. So limit S tends to 0 s times it was es, so instead of es we'll replace it with srs upon 1 plus g of s. So this is very important formula for steady state error. So now next we got a generalized formula for steady state error where r of s is the input. Okay, so if you want to calculate steady state error for any control system block, all you need to know is r of s, which is the input, and g of s is the control system, that block. Okay, so transfer function of that block g of s. So all you need to know is only those two values, you can calculate the steady state error. So then you can determine what is the accuracy of your control system. Okay, so the steady state error, it depends on type of input and type of system. Okay, so let's see how it depends on that with the help of examples. So we'll take three type of inputs. One is step input, ramp, and parabolic input. Okay, so let's see those examples. So now let's see how the steady state error depends upon the type of input. Okay, so first let's take step input. So the step input means r of t is a times u of t. So my r of s will be a into 1 by s, which is a upon s. Okay, so the steady state error will be limit of s tends to 0, s into r of s is a upon s, so upon 1 plus g of s. So this s will get cancelled here, so we get a upon 1 plus kp, where kp is typically we limit of s tends to 0 g of s. Okay, so this is called as position error constant. Okay, so this is the steady state error for step input. And for ramp input, this is the signal. Okay, so r of t is a times t, so the r of s will be a upon s square. Okay, so let's put r of s in this formula. Okay, we'll get the steady state error for ramp. So let me take another page. So for ramp, e of s is ess is equal to limit of s tends to 0 srs upon 1 plus g of s. So this will become limit of s tends to 0 s into a by s square upon 1 plus g of s. So 1 s gets cancelled here, we get a upon 1 plus a upon s into 1 plus gs. So limit of s tends to 0 a upon s into 1 plus g of s. So this can be written as a upon s plus s into gs. So since we are using limits s tends to 0, so this will become 0 and only we are left with here. So this can be written as the ess final value will be a upon let's say some constant. Okay, if we calculate limit of s tends to 0 for s of gs, we get some constant. Okay, let's say that as kv. So our steady state error formula, value will become this one, where kv is limit of s tends to 0 sgs. Okay, so this value kv is called as velocity error constant. Okay, so next let's see about parabolic input. So parabolic input means it will be in this fashion. So r of t is at square upon 2. So our r of s will be a upon s cube. Okay, so we'll substitute the value of this input in the steady state formula, steady state error formula. Then we get a what is the value of steady state error for parabolic input. Okay, so let's see that. So E of ESS, which is steady state error, is equal to limit of s tends to 0 s times rs upon 1 plus gs. Okay, so this will become limit of s tends to 0. Let's substitute the value of r of s. We get a upon s cube upon 1 plus gs. So 1 s gets cancelled. We'll get E of s is equal to a upon s square 1 plus gs. Okay, so there is a limit here, s tends to 0. So we can simplify it. Limit of s tends to 0 a upon s square plus s square into gs. Again, when you try to simplify this, so we are applying limit for whole of this. Okay, a is anyways constant. Since s tends to 0, we are calculating limit for that. This will go to 0. So only we are left with this limit of s tends to 0 for this s square into g of s. So this will give us one value, say one constant, which we can write it as kp. Okay, so overall the steady state error for parabolic input will be a over sorry, it is k, because we already defined kp for unit step input. So ESS is a upon k, where k is limit of s tends to 0 s square gs. Let me write that. Ka is limit of s tends to 0 s square into g of s. Okay, so this is the steady state error for parabolic input. So you saw how steady state error depends upon the type of input. Now let's also see the table and see how the steady state error also depends upon the type of control system, because we know that there are type 0, type 1, type 2, type 3 control system. Okay, so let's see the tabular representation of steady state error for different types of input under for various types of control system. Okay, when I mean types, I mean type 0, type 1, type 2. Okay, so let's see that. So this is the steady state error table. So it gives the value of steady state error, that is E of s, ESS, for different combinations of input and types of control system. Okay, so as you can see, for step input and for type 0 control system, the steady state error will be constant, and for any higher values of type, that is type 1, type 2, type 3, the steady state error will be 0. And same way, if the input is ramp and the control system is of type 0, then the steady state error is infinity. Okay, so you can relate that. I'll just take a simple example here. Say g of s is 1 over s plus 2. Okay, it means this is type 0. So the type of a control system means it will tell how many poles are at origin. So if no poles are at origin, that s is not at 0. In this case s is at -2. So how many poles are at origin will tell us the type of control system. So this is type 0 control system. Then my steady state error, you can use that formula, uh, that will become 1 upon 1 plus 1 over s plus 2. So there is a limit, s tends to 0 here. Okay, just hold on. So this is limit of s tends to 0, s into rs. For step input, rs is 1 by s. Okay, r of s is 1 by s. So this will become 1 plus s plus 2. So s tends to 0 means this will become 0. This is 1 by 2 is 0.5, 1 upon 1.5. So this is a constant. Okay, so for type 0 we got some value. Say let's take type 1. Okay, so type 1 means my g of s will be 1 upon s into s plus 2. There is one pole at a origin, so you can calculate the steady state error. I'll do it here. ESS is limit of s tends to 0 SRS upon 1 plus GS. Okay, so RS is step input 1 over S, so this will get cancelled, we get 1 here, and GS is in this case S into S plus 2. So limit of S tends to 0 1 upon 1 plus, this is, you replace here, S into S plus 2. So now just substitute value of s equal to 0 in this. Okay, so 0 into anything is 0 and 1 over 0 is infinity. Okay, so this whole thing will come to 1 over infinity. So anything which comes in infinity, 1 over infinity is 0, hence the steady state value is 0 for type 1. Okay, similarly you can calculate for any combination. So this is the steady state error table. Typically we calculate it for type 0, type 1, type 2, and for inputs step, ramp and parabolic. Okay, so you can see where we'll get the constant and where we'll get steady state equal to 0 and where the steady state error is infinity. Okay, based on this table. So students who are writing GATE ECE 2018, this is very important table. Okay, so there will be a lot of questions, first of all from control systems theory, and mainly the questions will be based on steady state error, calculation of steady state error involving step, and they'll ask what is the steady state error for type 2 control system, for ramp or parabolic, etc. So this table is very important, so you can memorize this. This is very simple, or you can remember this formula and calculate directly. Okay, so this is one of the most important concepts in control system. So we have tried to cover maximum in this video. So if you have any doubts, please use the comment section and let us know. Okay, and please subscribe to our channel. Thank you once again.